Mic check, mic check, mic check, mic check. Looks good. Mic check. Beautiful. Okay. So let's get this stream started. Where's OBS? Everything looks good here. Hopefully my audio is working fine. Looks good on my end. Today, on today's stream, I was really excited to do bare matrices, but somebody beat me to it. So let's see. I was going to do this exactly. I was going to do like a whole explanation, but then I saw this guy, which is a really good explanation. So instead of doing it from scratch, I'm going to encourage people to read this, which is a very good explanation of bare matrices, and then I'm going to cover all of the parts that I think are interesting and all the parts I don't know. So let's see. I actually haven't read parts 1 and 2, so I'm gonna. So the high-level explanation of bare matrices is they're used in rendering for dithering. So let's look at dithering. Dithering is a way of fading in and out that can be a little bit faster, or no, I guess it's not just fading out, but any kind of like gradient can be done with dithering. You can see here. This is a dithered image, so all of the individual pixels in this image are just black and white. But from far away, you know, they kind of merge together, and they give the appearance of grays because, you know, of how dense the white is against the black. That's the idea with dithering. And they're used a lot in games these days to do fading in and out. So if something is like it's in the background, and let's see, what's an example of a game that does this? I've seen The Witness do it. The Witness dithering. Let's see if we can get any screenshots from The Witness doing some dithering. And this screenshot is not high resolution enough to see. Probably none of these are. Oh well. Maybe this guy? He looks like he's dithering. What? Google image search, you're so weird. No, I can't really see any good examples there. But it's used a lot to fade things into the background because it's a little bit cheaper than drawing with transparency, and it has fewer edge cases than Uncharted 4 too. Apparently, yeah, it has fewer edge cases than fading because rendering a model with transparency, you have to sort the models back to front, and then like you get weird things where, there's sorts of errors where when you see them, like that's wrong. Dithering doesn't suffer from those problems because you're drawing it opaque, but you're only drawing every other pixel, that sort of thing. So that's what dithering is. And wow, this guy works. This guy is starting from the very beginning. I think I'm gonna probably skip. He's starting with quantized signals, which is important. But I don't think I want to get that far into it. Well, we will, having seen part 2, we will be talking about some frequency domain stuff, which is important and really interesting. Golden ratio sequence. I've never seen this. So, okay, I've never seen this. Let's see what this is. Sequence is made of the fractional part of next multiplications of the golden number. Oh, I see. Oh, so that's just a random number generator. Basically, you're using the fractional part of the random of multiple. Sorry, it's the fractional part of multiples of the golden ratio, and I guess we're using that to get some white noise. Oh no, but it looks like it has some kind of regularity in it, so it's not entirely random. Yeah, it's definitely kind of regular. It goes up a little, or maybe that's the problem with randomness. You never quite tell whether a sequence is random or you just appears to be random or whether it's not random and appears to be the other way around. So cool. Yeah, no, there's definitely a pattern here. Okay, so blue noise. I've covered blue noise in my videos before. Blue noise is noise with a lot of high frequency, but not a lot of low frequency, as opposed to white noise, which has power in all of the frequencies. And it's called blue noise because the blue end of the visible spectrum of light is higher frequency than the red end, which is lower frequency. So it's blue noise, like it has a lot of blue, meaning it has a lot of high frequency noise, but the low frequency, it does not have a lot of noise. And I think there's a picture of that in, later on in this series. Generating blue noise. Oh, that's an art, actually. That can be tough to do. So he has a technique for generating blue noise. Simple but brilliant. Step 1, let's take a noise with undesired frequency spectrum and just apply a high pass filter. That's one way to do it. Arbitrary high pass filter will produce a signal with very uneven histogram and completely different value range than the original noise distribution. Interesting. That's where part 2 of the algorithm comes in, remapping the histogram to force it to be in the 0 to 1 range. Interesting. Oh yeah. Sort all elements by value and then remap the value to its position in the list. And then you get a much better effect. Very cool. Unfortunately, histogram remapping operation also changes the frequency spectrum. This is inevitable as histogram remapping changes relative value of elements non-linearly. Values in the middle of the histogram corresponding to areas that had originally lost a lot of low frequency will be changed much more than values in areas with high frequency content. So part of the high pass filtering effect is lost. But still, it looks pretty good. However, there's some trailing low pass. But you just reapply the low pass. You just do the technique again. Oh, you do both steps in the technique again. You reapply the low pass, and then you do this reshifting operation that they did up here. The frequency spectrum definitely looks better, and the whole algorithm is very cheap. Well, I mean, you have to take it to the frequency domain, so it's not really something you do at real time, I don't think. But yeah. Fortunately, no matter how many times we reapply it, it's impossible to fix all of the problematic spots. That's fine. If some of the image contains only very low frequency, after applying a high-pass filter, we'll get few adjacent values that are very close to 0. After histogram remapping, they will get remapped again to similar adjacent values. All right, cool. What if we wanted some solution that doesn't contain local clumps? Then there's another algorithm. Okay, I want to get to the actual Bayer matrices, so I'm gonna skip over a lot of this, even though it is pretty interesting. So part three, bit quantization in 2D. When you encode your images in 8 bits, you are quantizing. When you encode your G buffers, you are quantizing. That's true. Even typical 8-bit is enough to cause some banding on very low, smooth, slow gradients like skies or lens flares. So we will cover a more extreme example, extreme 3-bit quantization of a linear gradient. Right. Okay. So I'm kind of maybe over-indexing on the usage of dithering for fading things in and out, maybe because that's what they use them for primarily at my work. There's no reason you can't also use it to do like smooth gradients like we talked about before, and that's what they're doing here. They're dithering this. They're basically just applying noise to get rid of this banding, and it works surprisingly well. I've done this. I had this banding problem in one of my games, and I applied some dithering. This is a very exaggerated effect right here, which, like, you can see visible banding, which with much less difference between the two, with much smaller steps in the colors. You've probably noticed it in some games, and when you apply a little bit of randomness here, dithering. Then it goes away. Like a lot of it goes away. So it's pretty like you can't even notice here you can notice the dithering, but if you do this technique, you do the dithering, you apply random noise, then then like you can't notice the banding at all, and you can't notice the dithering at all. So it's really great. So this looks better if you kind of stand back and squint, but it still doesn't look that great. So let's see, because clumping of areas identical one to one we've learned before and how we'll address it in post. Still visible bands of unchanged values. Yeah, like right there in the middle, where banding effect was not contributing to too much error. Oh, that's interesting. So this is the error visualized. So this, not this one, but this one right here is the error visualized, and it's showing how like, I think their scheme is that the more black or white you get, the more error there is, and so you can see right there in the middle there's a lot of gray, so there's not a lot of error there, but then it gets kind of black and white in these vertical bands right here, and that's where there's a lot of error. So that's what we're gonna try and fix, and step one is to do it by dithering more, and that works, but it's a lot more noisy. You can almost, like, you can't even tell the gradient now, honestly. So what are we gonna do instead? Using triangular noise distribution fixes those bands without over-noising the image. Triangular noise distribution, so that looks like a good PDF. Triangular noise distribution. Well, that's taking a while to load. Since this is a well-covered topic, it complicates analysis a bit. There are a lot of different distributions. I'll not be using this fix for most of the posts, so the bands will stay there. Okay, fixed dithering patterns. Now we're getting to the Bayer matrix. In previous part, we looked at the golden ratio sequence. It's well defined, but it doesn't work / is not defined in 2D if we want it to be uniquely defined. One of the oldest well-known and used 2D dithering patterns is the Bayer matrix, or ordered Bayer. It is defined as a recursive matrix of a sample pattern for level 0. Okay, so here's, let's see, 0, 1, 2, 3. Here's level 0. So this is the matrix, and I'll go over to... I think this is the matrix they do. 0, 1, 2, 3. Like that. 0, 1, 2, 3. So this is the matrix, and it means we're going to have a 1/4 coefficient out front. So, like, what they do is they take this matrix and they overlay it on the screen. Okay? So there's a pixel here, a pixel here, a pixel here, and a pixel here. And if the value, including this coefficient out front, if the value is like, you can test against the value here, right? So let's see, 1/4, this is 1/2, this is 3/4, and this is 0. All right. And right, so you can use this for testing. If the value is below it, then you go down. If the value is above it, then you go up. And this is a way of like, so let's see. Let's see if they have a picture. Yeah, this is it. So if I were to pass a 50%, let's say my test is, if the value if the value of the pixel is less than or equal to the value of the matrix, then make it white. I guess if it's less than or equal, then I should make it black. Otherwise, the value is greater than what's in the matrix, make it white. All right. Less than or equal to. You know what? I should do it the other way around. I should put so that we split it evenly. I should make this that less than and this greater than or equal to. So now let's apply this matrix to 50%. Like all the pixels on my screen are 50%. All right. So I'm going to start on the top left. Everything's at 50%. That's 1/2. And so the pixel is at 1/2, but the matrix is at 1/4. 1/2 is bigger than 1/4, so we're going to be white. We're going to fill in our first pixel white. Good. Now next, the matrix is 1/2. This is the matrix column, and this is the pixel column. Got to keep this straight in my head here. The matrix is at 1/2 and the pixel's at 1/2. So this square is going to be white too. I think I'm doing this right. Yeah. No, I did this wrong. Let's try again. Here are my 4 pixels. And they correspond to the, this one will correspond to this one. And this one to that one, and so on, okay? So my top left pixel, everything is 50% gray, 1/2. So the top left pixel, the value of the pixel is 1/2, and the value of the matrix is 1/4. So 1/2 is less than 1/4. So this is going to be black. Yeah, this is confusing. But this one, they're the same, so it's going to be white. The value of this pixel is 1/2. The value in the matrix is 1/2, so the bottom condition holds. Howdy, Kron. Wait, is that Jeff? I think that's Jeff. So with this one, the value of the pixel is again 50%. The value at the matrix is 3/4, and so this one's going to be black. No, I got this wrong again. Wow. It is Jeff. So no, this one's black too. And then this one. No, this one's black and this one's white. I cannot keep this straight in my head. Why is this so hard? I think this is correct. It's either this or opposite of this, but I can't keep the condition straight in my head. So it doesn't matter. Let's do a 4x4 matrix now. The matrix dimensions have to be 2 to the n. So you can only have 2, 4, 8, 16, and so on. So the matrix is defined recursively. I'm going to put a 1/16 out front. And then I'm going to start writing numbers in here. So I'm going to write the original pattern, 0, 1, 2, 3. And then my starting point is going to shift down to the right. I'm going to continue with that same pattern. 4, 5, 6, 7. So my starting point is following the same pattern, and actually I did that wrong. So the starting point for this guy is in the bottom right. So my starting point for this guy has to be bottom right. 0, 1, 2, 3. And then my starting point moves in this pattern. 4, 5, 6, 7. And then my starting point comes over here. 8, 9, 10, 11. And then my starting point comes down here. 12, 13, 14, 15. Hopefully that makes sense. This guy's kind of tricky because it's a recursion. I'll do it again. I'll try and explain it a different way. Because this matrix can be tricky. In fact, let me use a different but equivalent pattern to do it this time. Okay, this is going to be my new pattern. 0, 1, 2, 3. So my shape is like this. Right? And I'm going to apply this shape recursively. Okay? So my shape starts in the top left. Top left. So here's 0, and then 1, and then 2, and then 3. Just like that. So I do this, you know, top left, bottom right, top right, bottom left pattern in my matrix. And then I do the pattern again, except I start the pattern down and to the right. I'm moving down and to the right. So 0, 1, 2, 3, 4, 5, 6, 7. And then I move the start up. 8, 9, 10, 11. And notice every time I restart, I do the same pattern, but I do it larger over the whole matrix. And then 12, 13, 14, 15, and then I put my 1/16 coefficient out front. So that was fun. Let's do it with an 8x8 matrix. Oh my god. It's a huge matrix. It's going to be 2 to the 3 squared. That's 64. 1/64 is going to be our coefficient out front. Okay? And I'm going to use the opposite way as he did. He started in the bottom right, but my brain doesn't like that. I'm going to start in the top left. Because I think I like this way better. So the same pattern, 0, 1, 2, 3. I did the same pattern right here. Now I'm going to move my starting point down into the right and do 4, 5, 6, 7. Now move my starting point up here, 8, 9, 10, 11. Then move my starting point here, 12, 13, 14, 15. So my starting point went like this. But this is Bayer matrices, and it's used in dithering. You know, it's used a lot in rendering for. I'm following this tutorial. So we're making this matrix right here, a Bayer matrix, and we are going to apply it to get this sort of gradient, or we can use it to do fading things in and out instead of drawing with alpha. So that's what we're doing. So now I've drawn, you know, it's equivalent to this matrix. It's equivalent to this matrix, and I've drawn it. I have a permanent eraser now. I've drawn something equivalent to this matrix inside of this matrix. But I still have, like, all of these are empty spots in my matrix that I haven't actually put any data into yet. I still have to fill all of those in. And I'm going to do so by taking this whole pattern that I've started with here, and I'm going to duplicate the pattern. Like this template, I'm going to duplicate it 4 times in this same pattern. I'm going to draw it here, and then I'm going to draw it here, and then I'm going to draw it here, and then I'm going to draw it here. All right, it's recursive. It's recursive. So instead of changing the starting point by this pattern, I'm going to change the starting point of the starting point by that pattern. Okay, so my last number is 15. I wish I could get rid of this eraser. It's annoying. I don't know why it's still there. There we go. Okay, so let's start. So let's start with 16. So 16, 17, 18, 19. Hopefully I don't screw this up. 20, 21, 22, 23. And now I start here. I'm following this pattern. 24, 25, 26, 27. And now I go down here. 28, 29, 30, 31. Okay, so I've finished half of the whole matrix. So half of the highest level recursion has been finished. So now I start again right here. So before, this was my pattern. Well, first of all, this was my pattern. See, 0, 1, 2, 3. My pattern started with 0, 1, 2, 3. Now my pattern, I just finished a pattern that was smaller, 0, 4, 8, 12. And now I'm going to do the smallest pattern. This matrix is so amazing. It's so weird. 0, 16. And now we start at 32. Oh my goodness. So 30. So now I go back to drawing the big pattern. 33, 34, 35. So now I'm going to draw this pattern. 36, 37, 38. Oh my goodness, I'm going to get lost here. You know what I'm going to do? I'm going to back up, and I'm going to put all the numbers starting at 32 in a different color. 32, even more different color. 32, 33, 34, that'll help me keep track of where I am. 35. So now I'm doing this shape. 36, 37, 38, 39. Now I go up here. 40, 41, 42, 43. And now I go down here. 44, 45, 46, 47. All right. So I did this template. So hold on. First I started with this template, and then I did this template, and then I did this template, and now I'm going to start with this template. So where was I? 47, 48, 49, 50, 51. So that was this guy. And now I'm going to do this guy. 52, 53, 54, 55. I'm going to do this guy. 56, 57, 58, 59. And now I have to finish right here. 60, 61, 62, 63. I didn't lose track of my count or anything. Great. Amazing. Okay. So now that I have this big matrix, I want to see if I can start filling in some of the pixels. Okay. I think in the article, we have, yeah, this is an 8 by 8. So this is like this is the actual color values that you get if you multiply through by this coefficient right here, and then just use that as color values. But I'd like to see what happens if we take this and use it as just a filter for like exactly what we did before. Everything is either like less than or greater than. We gotta organize my thoughts here. Bayer matrices are usually are used for like creating noise because you have like you only have this color value and that color value, and you want to simulate all of these color values, right? So it's used. This is why the first part of the article is about quantization. It's used to decide how to quantize these values. Everything here drops down and everything here drops up. So I'm going to do that with this picture. Everything below 1/2 will go to black, and everything above 1/2 will go to white. That's a much easier way of thinking about it than I was doing before. I don't know why I was doing it that way. So I'm going to partition my grid into an 8 by 8 structure right here. Keeping an eye on chat. That was a terrible line. Terrible, terrible line. This is why I'm a programmer, not an artist. I wonder if Mischief has a way of drawing straight lines, but it doesn't matter. Now I'm done. It probably does. Okay. So I'm going to just go through each of these squares and fill it in if my value is greater than or equal to half of half, 1/2. Yes, this is dithering, dithering with Bayer matrices. So 0, so this guy is black. This guy gets white because 32 is exactly 1/2. 8 over 64 is less than 1/2, so it doesn't go in. 40 over 64 is bigger than 1/2, so this guy becomes white. 2 is less. 34. 42 is greater. 48 is greater. Okay, so that's an interesting pattern. It basically looks like a chessboard now. Which, I mean, it's not really all that unexpected, is it? That it should look like a chessboard. It's a pretty regular pattern. I think this pattern is pretty much... hold shift. No. Hold command. No. Hold control. Hold option. Oh. Not option. Hold function? No. It's almost the same pattern as the colors and the numbers. Yeah, that's true. Like the green ones turn into white, and it's exactly the same pattern. So I made this, pretending I continue with all of these pixels. I made this by saying, okay, this cutoff is at 1/2. But if the cutoff is like here, then we might have a different result, right? So I'm gonna erase all of this. I'm not gonna erase it because it will take me forever to redraw the grid. So I'm just gonna undo. There we go. So now I'm gonna say, what if my cutoff is 1/4? Now let's see what the new value is. And this is the last time I'm gonna do this. I just wanna. So let's see, 1/4 of 64. What is that? 64 divided by 4.
It's 16.
16. I should have been able to do that in my head, but... So anything, let's see, 16. Anything greater than or equal to 16 will turn white, basically. So this will turn white, this will turn white, this will turn white. Oh, this entire row will turn white. So here's our pattern. So this makes a pretty regular pattern, basically. Looks like that. It's pretty. It's a pretty pattern. So until this guy posted this this article on Bayer matrices, which is really great, I couldn't find any general formulas or code on the internet for generating arbitrary Bayer matrices. And here it is. Here it is right here. When I announced that I was going to do Bayer matrices last week, this formula didn't exist on the internet, and I was going to write it. But he beat me to it. He wrote it, and not only that, he wrote it in a different way than I was going to write it. So what I actually think I'm going to do is I'm still going to write my version of the algorithm, and then we'll come back to this version and see how this version works. They're both recursive, but I had a slightly different idea of how to do mine. So let's see. Let's open a new project here. Can we just... Let's just close this. Is all of this saved? No, let's do this. New project. New project. Come on, Sublime. I don't know how to use Sublime. Okay, we'll just close this project. Alright. And save something to, I don't know, somewhere. Make a new folder here. New folder, please. New folder. New folder? New folder. Bayer matrices. Good. Save. And we'll add this folder to our project. Bayer matrices. Good. Okay, and make a rename this file to something that makes sense. Bayer, come on. Bayer.cpp. And then I'm come over here to my console and say Bayer matrices. Okay, and then I guess what? GCC will work. Wow. Oh, I don't have a main. Good. Main. And we don't need any arguments. Okay. So we're going to write some code to generate a Bayer matrix. Good, that compiles. And what does it do? A.out. Good. Oops. So we're going to build it with debug symbols. So how are we going to do this? How are we going to do this? So actually we need some kind of input here. So we need to know, like, what is the size of the matrix? Matrix size. So that we can parameterize by that. And we'll start with 4 for now. Okay. So now I'll, let's see. We'll use integers for this. So I'm going to make my actual matrix, the matrix. And matrix size, I'm going to have to make it like this. All right. So that will allocate our actual matrix. And now I'm going to need to say, so this is going to be my Bayer function that actually fills in the matrix. I'm going to need the matrix, and then I'm going to need some other parameters here. I'm not quite sure yet what they are. So we'll pass that into the function, and then I guess we need to know the matrix size. We're going to need to pass the matrix size into the function. So the matrix size. Okay. So each level of the algorithm is going to place, is going to recurse. Let me draw a picture of how I'm planning for this algorithm to recurse here. Okay. So the topmost level of my algorithm has to recurse like this. Okay? It can't recurse like that. Like you want to recurse like this. You want to start by placing the 0 and then place the 1 and then place the 2 and then place the 3. But I think you have to start here on the inside. And I'll show you what I mean. So Bayer, let's see, 0. I'm just going to call it B instead of Bayer. I don't want to have to write Bayer all the time. So this guy will be B of 0. And then, you know what, let's do this. Let's parameterize this once more. So we're starting at the number 0, like we're going to write the number 0 first, and then this is the first level. And then in this recursion, all of this is going to be part of the same recursion. We're going to write the 0 first, except we're going to start at the second level. And then we're going to do it again, except we're going to write 16. So we're going to do this little square right here. 0, 16, 32, 48. So 16 as part of the second level. And then we're going to do it again, write 32 as part of the second level. And then, etc. 64 as part of the second level. Okay, now we're going to recurse again. So we're going to write 0 as part of the third level. And then, so now we're in the third level. We recurse like this. First we recurse like that. Then we recurse like this. So now I'm going to write 0, 4, 8, 12. 0, 4, 8, 12. Okay, so I hope this makes sense. I hope my strategy makes sense. I'm like, my highest level recursion skips over a bunch of numbers. And then when I get into the smaller level recursions, I skip over fewer numbers. And then right here, this is going to call B0, 4, and then B1, 4, and then B2, 4, and then B3, 4. And that's how it, you know, it'll know it'll be done, because it's, you know, its stride here is 1. So that means it can stop recursing. Its increment is 1. I should get consistent with my terms here. I'm going to call the difference between these two numbers, let's see. I'm going to call like the amount of separation between placing numbers. This is stride right here. Stride, meaning I'm placing numbers adjacent in the matrix, so my stride is 1. Whereas if I place numbers separated by 4 slots in the matrix, then my slide is 4. So when my stride is 1 and I'm placing adjacent numbers in the matrix, then my increment is 16. So this number right here is I'm going to call the increment. Okay, so my increment is 16 when my stride is 1. So then when my stride goes up to 2, my increment falls to 4. And then my stride goes up to 4, and then my increment falls to 1. So that's the like, there's an inverse relationship between stride and increment. But I should be able to calculate stride and increment if I have this number right here, my recursion level. So let's give that a shot. Int recursion level. And I'm going to start, in the example I started with recursion level 1, but now I'm going to start with recursion level 0 right here. So this should really say, if it's going to match what I'm about to code, 0, 1, 1, and this will be 2, 2, 2, 2, 2, 2, 2, and then this will be 3, 3, 3, 3. So my recursion level starts with 1. So let's see. At recursion, I'm sorry, it starts with 0. At recursion level 0, that means my stride is going to be 1. So this is my recursion level. and this is my stride. At recursion level 0, my stride is 1. At 1, my stride is 2. At 2, my stride is 4. So it looks like this formula here is that my stride is 2 to the recursion level. That looks right to me. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So I can calculate my stride using my recursion level. And same thing with increments. If I have my recursion level and then my increment, okay. When my recursion level is 0, the stride is 4. And then 1, 2. So this is just the opposite. This is literally the exact opposite we just did. So the increment is equal to 2 to the n minus r. Did I do that right? Not n, because n is like my maximum recursion level. Let's not use n as the maximum recursion level, because n is like n should be the width of the matrix here, which is 8. So we should say log, come on. So n is 8 in this example. 1, 2, 3, 4, 5, 6, 7, 8. So the question is, how many recursions are we going to have when n equals 8? And the answer is log base 2 of 8, which is 3. So I think that's what goes right here. So let's get a little more space. I is going to be 2 to the, this is how many recursion levels I have, oops, minus r minus 1. So let's see if that works. Let's see if that works. This is a little more complicated, but it's I'm writing a recursive algorithm for a Bayer matrix, which is used in, you know what? Let me do this. Let me take this guy and go to the Twitch. My Twitch channel. And can I put this in like the description or something? That's the title. I'll just put it right here. Today. That. And I'll put it in chat as well. Okay. So there's a quick summary on that page for you to get what's the word, acquainted with what we're doing here. Okay. So this is a lot, like, this looks crazy, but all it is making it so that instead of, okay, so when, let me do this. 0, 1, 2. Now let's see what log base 2 of 8 minus r minus 1 is. When r is 0, then we have log base 2 of 8 is 3 minus 1 minus 0 minus 1 is 2. Now when r is 1, then we have 3 minus 1 minus 1 is 1. And then when r is 2, we have 3 minus 2 minus 1 is 0. Right? So I've just reversed the order of the numbers here using this little trick. So that instead of going 0, 1, 2, they go 2, 1, 0. And then that will let me do this, make it, you know, what I need is I that does the exact opposite of what it did before. It goes 4, 2, 1 instead of 1, 2, 4. And I have that now because I reversed the input, basically, the input. So 2 to the log base 2, 8 minus r minus 1 will be 2 to the 2, which is 4, and then 2 to the 1, which is 2, and then 2 to the 0, which is 1. So that's I. So that's what we want. So now we have formulas for calculating the stride and the increment given our recursion depth. So good. So let's go back to the code and implement those formulas. So let's start with the stride. The stride is 1, 2, 4. No, sorry, the formula. 2 to the R. 2 to the R. I'm going to implement this by using a left shift. Super easy. Recursion level. There we go. And let's do the increment. And now I have to do, how am I going to do a log base 2? How am I going to do a log base 2? Of 4. So I have this matrix size parameter, and I want to know how many times do I divide that by 2 before I get to 1. But there's got to be a fast way to do this. I don't want to actually have to run like the log function. I don't want to have to say log of matrix size divided by log 2. So this is like the, let's see. Like this, you know, log base 2 of matrix size is that, right? And then I can calculate my increment by saying, well, 1 left shift log base 2 matrix size minus recursion level minus 1. But I don't know, this is not a very efficient way of doing it. Yeah. That's what I'm trying to avoid. I'm trying to avoid explicitly doing like all of these logs or a loop. I could do it with a loop. Why not use the slow one for now, and if it's a problem, use something faster later. That is definitely an option that I can do. Oh my god. Oh, it's so simple. I can use an array. I think I can use an array. Okay, and I'll show you what I mean. Because I know that my matrix size is a power of 2. It must be a power of 2. Okay, so I don't really have... No, I can't use an array. Quick optimization would be to cache the levels in advance. Yeah, that's what I'm saying. That's what I'm saying. Yeah, like a lookup table. A lookup table, except... Like my table would be, okay, you know, there's a value for 1 and it's 1, and there's a value for 2 and it, wait, is it? No, it's 0. There's a value for 2 and it's 1. There's no value for 3. There's a value for 4 and it's 2. There's no value for 5, 6, or 7. See, so it's sparse. And here's the value for 8. But this will still work if I use, instead of passing the matrix size, I pass like int n. N equals 2, and then matrix size is 1 left shift n, and then I pass n instead of GCC uses a lookup table for log for numbers less than 1,000 or something. Yeah, but I think doing this I can now avoid the lookup table completely, because now my lookup table looks like this. Yeah. Because now I'm using n instead of the matrix size, right? So I can say table n. Will that work though? Log 2 matrix size equals pop count? I don't know what pop count is. Maybe there's like a bit fiddling way of doing this. I'm gonna look at that Stanford bit. What was it called? Bit twiddling. Yeah. This page is great. Finding integer. Oh, I see. I've tried to do this before. See, this is what I want to avoid the loop. Find the integer of an integer. See, I don't want to do the float either. Oh, wow, that looks really hacky. No, I don't want to do that. And this is undefined behavior land. I don't want to do that either. Yep, table. Yeah, so this is the sparse table problem. This is what I want to avoid. I don't like that either. And oh, see, I don't want to do that either. Okay, yep. I'm going to avoid the log by knowing the number magically in advance. Wait, I don't even need a lookup table if I do it this way. Because n is the... So 2 to the 0 is 1. So 0... 2 to the 1 is 2. Yeah, so n is my answer. It's just... It's not even table n, it's just n. Right? Because I do 2 to the n here in order to get the matrix size in the first place. And so the inverse of that is log... Yeah, maybe premature. Maybe premature. You can whistle all you want. Well, let's continue. Let's actually get through here to what we want to do. So we've got our stride and our increment. So we can start placing values into the matrix here. So let's see. I'm going to get some coordinates for myself. Now let's just do this. Matrix. So then we have that. So oh, I'm not getting into an argument about premature optimization. You guys can have fun. Okay, okay, so if my increment is 1, then I'm going to be filling values into my matrix. So, but I'm not even going to worry about that yet. I'm going to worry about the case where I'm still recursing. So let's do this, matrix n, and now recursion level +1. And you know what? I think I need one more parameter in my happy function here. It's a happy function because I was watching Bob Ross. I need like a start number, a number to start at. So now this is what the increment is for. We say start plus increment, and then just add a lot of these. Start plus increment times 0. Start plus increment times 1. Times 2 and times 3. So that was the whole point of the increment right there. You know what? I don't think we even need the stride until we've started to write stuff. We totally don't. Yeah. Because all we care about is the recursion level. Okay. No, maybe we do care about the stride. Yeah, because this is the starting number, and then the starting number gets incremented. But that doesn't tell us the starting position, so we also need to know the starting position. So let's do this. Start number, and then we'll pass in an x and a y. an x and a y here, which starts at 0, 0. So when we recurse on this x and y, this is going to stay here, but then we say x plus stride, y plus stride. And then, so we do need to know this stride. And then, let's see. We keep with the x plus stride, but we don't do the y plus stride. And now we do x, but we do the y plus stride. First, it has to work. I mean, you're both right, you know. When you build a house, do you build your house half-assed to make sure it's the way you want it, or do you build it right the first time? Performance is an important consideration, and but it's not the only consideration. In this case, I'm concerned about performance because I don't want anybody looking at my algorithm being like, "Hey, dude, it's not very performant." Especially when it's like this straightforward. I don't think I've made anything terribly unreasonable to read in the performance considerations that I've had. Nope, I'm out of this conversation again. I'm just going to finish the algorithm here. I'm going to finish the algorithm and then we can talk about how performant it is. I honestly don't even think... So we're talking about performance, and that's the problem, because I don't think I'm writing the most performant algorithm in the first place. There's a definite pattern to the numbers here, like 0, 32, 840, 234, 10. Like these are... It's like plus 32 minus... what's 32 minus 8? Minus 26. Plus 32 minus 26. Plus 32 minus 26, right? There's a pattern there. That's not the pattern. But there is a pattern here that I could probably exploit and by doing so, write the entries of the matrix in order, which would be a hell of a lot more performant than jumping around in the matrix like I'm doing right now. It would be like cache efficiency is probably the biggest concern here, which is why I think that the way this guy did it, this looks like it exploits that pattern. So this guy's probably more efficient than I'm being here. So I guess I shouldn't worry about it that much. It's no big deal. All right, let's just write our stupid matrix here. Okay, matrix. We're ready to write into the matrix. The matrix size we don't need until we're right here. Okay, so x plus matrix size times y, and then equals start number. So now our increment is 1, so we just do like this. Start number plus 1, plus 2, plus 3. Make it nice and even. Okay, but now our stride is really big. So we should probably do like this. X plus stride. Y plus stride. Got to do it the same way here that I did it below. And then y plus stride. All right. Think that'll do it, actually. Let's print it out. I hope I don't have an infinite recursion here. Yeah, I'll do it this way. Why not? I need another index. Why did I do this? So we're just going to print out the whole matrix. X plus matrix size times y. Print all that out, and then print a new line. Bam. Uh-oh. So save, and then do my amazing compilation. Ooh, I have an error. So matrix and recursion level, start number, x, y. All right, compile it. Really? Oh, yeah. Compile errors. Unidentified use of printf. I should probably import the stupid header file. Where is it? Come on. stdio.h. Yeah, my inner loop. Thanks, Jeff. All right, now run a.out. Looks like it works. 0, 1, 2, 3. 0, 1, 2. Oh, I transposed the matrix from. Oh no, it didn't work. I have two 2s. That's wrong. So 0, 1, 2, 3. 0, 1, 2, 3. That should be a 4. 5, 6, 7. That should be an 8, 9, 10, 11. So I have 2 6s and 2 7s. Yeah. So there's a little bug in here somewhere. Little bug in here somewhere. Where is it? Where is it? So my increment. Is my increment correct? Well, time to run a debugger. Hopefully this works. Oh, good. It does work. Okay. So we make our matrix. Oh, of course. No, that's not it. So start number 0. That's fine. Start x and y. Yeah, it probably is a fence post error. 0, 1, 2, 3. 0, 1, 2, 3. No, well, it's off by 2, not by 1. I think I just got the wrong power of 2 for either the increment somewhere. That's my guess. So let's see. Let's see what our increment is here. Should be, it's 2. Should be 4. Yeah, see? So log 2 matrix size is 2. Minus recursion level is 0. 2 minus 0 minus 1 is 1. So that's 2 to the 1, which is 2. But it should be 2 to the, and 2 to the, let's see, recursion level 0. It should be 4. So it's, I think this minus 1 is wrong. How's that possible? Yeah, because this should be, oh, because I'm passing in n. Yeah. So my n was off by 1 of where I thought it was, which is fine. I didn't really think about n too much, so I made an error. It's hard to code on stream, man. I'm not trying to make excuses, but... Oh, now I got a seg fault. Ooh, that's interesting. Where's my seg fault? Did I overwrite the array somehow? I overran the array. My matrix size is 13. That's not right. 1 left. Matrix size 13? How's that possible? 1 left shift 2. Matrix size is 4. Matrix size is 13. What? When did it become? It's 4 now. It's still 4. Oh, I overwrote the array and I must have written a 13 into the, like, the next. spot in the stack. I must have overwritten the array here somehow. How's that possible? Oh, because I recursed too much. Okay. So let's hop in here. So my increment starts at 4. And then my recursion level goes up by 1. And now my increment is 2. And now my... Wait a minute. Was my array the right size? No, it's 4 by 4. That's right. That's correct. Okay. So I should be doing... I should only have one level of recursion. Now I'm confused. Yeah, I should only have one level of recursion here. So actually my increment should start at... Yo, my increment is way wrong here. Isn't it? At recursion level 0, my increment has to be 16. Oh my goodness. So wrong. I did the damn math wrong. Okay. At increment... At recursion level 0, it should be 16 because I go... My increment should be 16 because I go 0, 16, 32, 48. So there's my problem. And then it goes down to 8, and then it goes down to 4. Yeah. So this... Increment level is 4. Hold on. Let's not jump the gun here. Let's not jump the gun here. Oh, that's such a good idea, actually. No, wait. Collab code. Come on. You know it. Collab edit. New document. My name, George. Yeah. Can it compile? I wonder if there's one where you can collab and compile at the same time. So let's see if I can paste this into chat. It's a pretty good idea. Pretty good idea. Okay, so I think when the increment is so hold on. When the increment is 4 is when I'm done with the recursion. That does make sense. Yeah. Can you see if you can find me one with a compiler? Because this one's cool, but collab edit. No. Yeah, so if someone can see if they can find me one with a C compiler, that would be great. Or C++ compiler. We'll try and use that. I'll power along here. So yeah, so I think when this should be 4 right here. And then start, yeah, because the increment here is 4, 0, 1, 2, 3. So this one you write the start number, and this one you write the start number plus 3, and so the next one after that is 4. So I think that's right. Codebunk.com. Let's try it. No sign up required? That's good. New bunk. All right. We're doing a new bunk. My display name. Editable by me alone. Boo. And can I hold on, I'll log in if I want. Oh, I don't want to log in. Python. It's Python, you guys. C++. Oh, no, thank you. Okay. Run. I'm running the code. Oh my god. Oh. Oh, that's wrong. Well, that's fine. Okay. I guess I have to log in or something. Me home. What do I do? Oh, I just ruined it. I guess I have to log in. How do I log in? Want to log in. I click the drop down. What drop down? I'm so bad at the internet. This drop down? That thing dropped down. That's not what I wanted. Let me just go to codebunk. It tells me to log in, but it doesn't give me a place to log in. I don't really want to log. I don't want to have to create an account just to do this stupid website. But I guess I will. Now everybody knows my email address. Not like I haven't posted it on the internet a million times already. Okay. I have 5 collaborative sessions remaining. Oh man. I can only do this 5 times? Well, then I have to buy more. Let's create a bunk. I think this website is bunk. Rate candidate. End interview. I can tell what this is for. Okay. I think it's public now. How do I share it? How do I share it? Share it, share it, share it. Use session. I'm gonna use one of my sessions. Oh, it's on a timer? They really want my money, man. Okay. So now it's on a timer. Is it gonna give me a link that I can link you guys from? Oh my god. No links here. No links there. Link up. Oh, maybe this will work. Try this. Try this, Twitch. Let's see. Let's see if we can do this in 120 minutes. I hope so. Oh, I see some more people. Here's Dougal. Okay. Okay. So I'm going to run this. It's not going to work. Yeah. So 0, 1, 2, 3 worked, but the rest, this is probably uninitialized data right here. So something's still wrong. No, this is not even supposed to say 0, 1, 2, 3. This is supposed to say the 1 is supposed to be here and the 2 is supposed to be... Okay. So I'm gonna copy this over here just so I can use the debugger on it. And we are writing an algorithm that makes Bayer matrices. I think I tried to put a description of Bayer matrices in the description. Look below. Coderpad.io. They really like are indexing really big on this interviews thing. This is, I don't care about interviews. But pick a language. I'm not a candidate, but that's fine. Run. Alright, more uninitialized memory. That's good. That's good. So let's see. Oh, good. This is private. We want to make it public? Public. Public. Good. Code execution enabled. Okay, that looks fine. That's free for 7 days. Oh, good. I guess it's hard making this kind of software. Invite. Share link. It's paid. Yeah, maybe let's not do this one. Let's stick with this one. Let's stick with the code bunk. It works. I don't want to hop around too much. We'll close this one. The code bunk one is working for us, I think. Maybe I'll try and find. I don't know how much I'm going to be able to do this, like where all my coding is in one file on stream. But if I plan on doing it again, I'll definitely find one that I can use. So anyway, where were we? That's not paid. They're probably all paid, to be honest. But okay, so what is my stride? My stride is 1. That's good. My stride should be 1. My increment is 4. Whoa. That's not what I want. Well, no wonder. Okay, so I think I just have to finish this math right here. I'm not gonna try more stuff. I'm done like trying stuff. If you can find something that you're sure is not paid that we can all get into easily, preferably without logging in, and compile C++, then like if you're sure of all of that stuff, then let me know and I'll check it out. But yeah. But we'll go with this one for now because I think it will do everything that we need to do. Code bunk. So when 0 I need 16, when 1 I need 8. So I think I still need a 2 to the something. 2 to the, I'm going to call it k. Okay, so here I need k equal to 2 to the 16, 2 to the 4. Here I need k equal 2, here I need k equal 1. Okay. Oh. No, this is 3. This is 3. What am I talking about? I can't do math. This is 3 and then 2. Yeah. So 2 to the 2 is 4, and 2 to the 3 is 8, and 2 to the 4 is 16. So good. So then I can still use this guy. Okay. So log base 2 to the 8, that's 3. So log base 2 to the 8. 3 minus recursion level starts at 0. 3 minus 0, but then I need a plus 1. This needs to be plus 1. I think that's it. Okay. Well, no, let's just start with this. Log 2 to the 8. Log base 2 of 8 minus r plus 1. So this is 3. This is 3. So 3 minus 0 plus 1 is 4. 3 minus 1 plus 1 is 3. Yeah, so this is what I want. And 2. Okay, so then if I do 2 to the log base 2 of 8 minus r plus 1, then 2 to the 4 is 16, 2 to the 3 is 8, and 2 to the 2 is 4. So here's our formula. Yeah. So I just need a plus 1 here, and that will fix all our problems, I think. Oh, let me put it here instead. Plus 1. Run. It's taking a while. Ooh, that looks good. 0, 1, 2, 3, 8. Oh. Now the increment's wrong. I don't know. This might be a good interview question. That's all I'm saying. I'm having some trouble with it, but I'm pretty dumb, so. 0, 1, 2, 3. So let's go back to the debugger. All right. So to start with, our stride is 1. That's what we want. And our increment is 8. Nope, that should be 16. Why? Oh. is log 2 of the matrix size. Matrix size is 4, so this should be, oops. This should be, nope, that should be 2. That's correct. Log base 2 of the matrix size, which is 4, is 2. So 2 minus the recursion level, which is starts at 0. And then plus 1, so that's 3. So 1 left shift 3, that gives us 8. No, and 8 is correct. 8 is correct because this is a sorry, this is a 4x4 matrix. So let's see what the code was giving us here. So 0, 1, 2, 3. No, but it should be 4. Yo, I'm so bad at this. Okay, so then this is correct. No, the increment should be 4. The increment should be 4 here. I did something wrong over here. Okay, let's do it for the matrix we actually have. When it's 0, it should be 4, and it's 1. When it's 1, it should be... When the recursion level is 1, it should be 1. Sixteen, 4, 1. 16, 4, 1. So anyway, this should be 4, not 8. So this is 16, 4, 1. Not 16, 8, 4. Oh man, attention to detail. 16, 4, 1. Yeah, so this whole thing is wrong. This whole thing is wrong. Let's try again from start. I gotta slow down. I gotta calm down and slow down here. 0, 1, 2. And this is the increment we want. 16, and then 4, and then 1. Ah, so this is why I was getting it wrong before. So this looks like 2 to the 0, and this looks like 2 to the 2, and this looks like 2 to the 4. So there's a factor of 2k here that I forgot. So this is like 2 to the 2k, where k is 0, 1, 2. K is, is 2, 1, 0. So here's our new formula. 2 to the log base 2 of 8 minus r minus 1. And then all of this times 2. If you use Chrome and Hastebin, check out use Safari. All right. Thank you, Jeff, for spinning up a Cloud9 instance. So I think this will get us what we want. So this will be 2 to the 3 minus 0 minus 1. 3 minus 0 minus 1 is 2, so 2 to the 4. That's 16. Yep, this is it. This is it. We got it. We got it. Here we go. Here we go. So we need to move this back to minus 1. And then we multiply all of this times 2. Bam. Done. No, not done. Probably not done because I need to fix up some other stuff that's now broken because of that fix. But we should be able to do that real quick. So the first increment is 4, which is correct. And the stride is 1, which is correct. All right. Oh, see, and now, yeah, see, that's the thing. We want to change this increment back to 1. See, so we made that other fix. Now this increment should be 1, and that should make some progress anyway. It might fix it, might fix the whole thing. Yeah, okay, so this looks good. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That looks good. That feeling, man. That feeling. Okay, let's pump it up. We're going to get Hans and Franz on this bitch. 0, 1, 2, 3, 4, 5, 6, 7. This looks good. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yeah, this all looks good. So this is it. And so we got 32 there. Yeah, so okay. So here, we got all our patterns. 0, 1, 2, 3. That's the big pattern. Then our next level pattern is 0, 4, 8, 12. And then our next level pattern is 0, 16, 32, 48. All right. We're going to continue to pump it up. Oh, okay. We got a Cloud 9 instance just in time for us to be done with this thing. Let's hop into that. Okay, I guess we got to sign up. Sign up for an account. Have to give it my email address. Everybody knows it already. Hi, good to meet me. My name is George. My username? I don't know if I should do this while the stream is watching. Okay, yeah, I'll do it on the other computer. Doing it on the other computer where people can't see. Yeah. All right. Here's my name. My username is... Usernames must start with a letter. Only lowercase letters and numbers are allowed for some stupid reason. And that one already exists. Let's try another one. What kind of developer are you? I'm a student. How will you use Cloud 9? I don't know. Credit card details? No thanks. Why is it asking me for my credit card details? Oh man. Okay, hold on. I have to give it my credit card. What if I don't have a credit card? A family member. Oh yeah, just ask a family member or friend. I don't know if this is gonna work. Some people don't have credit cards, and I want to like prevent them from using the stream. Yeah. Yeah, well, we're almost done here. We'll find a solution that works later. Where's my code bunk? Here we go. Okay, let's check this one real quick. So here's 0, 1, 2, 3. So that pattern is good. 0, 4, 8, 12. That pattern is good. 0, 16, 32, 48. That pattern is good. 0, 64, 128, 192. Okay, cool. So I think we made a working algorithm. Now, all of my mathematics training means that the first thought that popped into my head when I wrote this algorithm is, prove that it's correct. Yeah, 100 levels to get started. You can't just like hop into a thing and start writing code with other people. It doesn't work that way for some reason. They have to get your credit card before you can start writing code for people. So let's see. So this is pretty good. This is a 16 by 16 Bayer matrix. Should have 256 values in it. How would I prove it's correct? I mean, it's kind of correct by construction, isn't it? The one that you would have to prove is correct is this one. Because this one does some different stuff. This one does some different and clever stuff. So let's implement this one. I'm going to copy it in over here. Where is the thing? I'm going to copy it in over here. Bear 2. Int x, int y, int level. Alright. And, you know, First, I have to try and understand this. Because, wait a minute. There's like an x underscore here, but they don't refer to x underscore anywhere in the... I'm just going to assume that that means this x. Maybe not. What's going on here? So let's comment that out. And then try and make a new version that actually looks C or C++. Can we profile with gprof so we can see what's slow? With the algorithm I did before? I mean, I could, but I don't know. Is it worth it? Also, it's a recursive algorithm, so it will tell me that 100% of the time is spent in the Bayer function. You know, which is true. So bit right shift. So that is, I hope that this is what it meant, bit right shift. And then mod that with 2. And then +1. Okay. Bit right shift again. So I think we're going to do this. Move that. And then mod that again with 2. Mod that with 2. And so this whole thing gets modded with 4. Plus, if. Huh. He's using some really weird notation here, which I don't want to do. So I'm going to say, I'm just going to start making some temporaries here. So this is a number. I don't know what number it is yet, but we'll figure it out. We're going to learn this as we go. So then I'll say if, I think this is what this notation is supposed to be. If level equals 0, then we have number plus 0, I guess? Otherwise, I screwed up the... Okay, otherwise, number plus 4 times Bayer 2, and then we start recursing. And then we do that. I guess it's supposed to return? Or... right? See, but it never actually, like... So what does this do? Maybe it just generates a sequence of numbers. Maybe it just, like, yields numbers. So let's do this. I'm not quite sure where it's supposed to be going with this. No, that can't be it. I don't think it's a yield. What is it doing? This is like, where's the page? It's like a recursive formula, I think, that that defines the value of each pixel. But I don't know. I guess if level equals 0, yeah, so that must be it. So So the way we do Bayer 2, I think, where's the code? Yeah, that's the way we do Bayer 2. Yeah. So the way we do Bayer 2 is a little bit different than the way we did Bayer 1. So let's comment this guy out. Okay. So I think the way we do Bayer 2 is we loop over, please scroll down. We loop over each index and we call Bayer 2 for that index. Yeah. It's like, oh, it's Mathematica. Oh, I've never used that syntax before. Yeah, so you like, I think what we're doing here is we're kind of looping over each one, and then we're setting, you know, matrix at this point, the value at this point should be Bayer 2 xy. But what do you put for level though? I don't know what to put for level here. Something. Okay. I think this is the idea. Like you loop over the matrix, and for each entry in the matrix you say it is equal to this. But then you have this recursion on the level. If the level equals 0, then return number. Yeah. You know what? So then really, like, I think it's doing the same thing that I did. I thought it was doing something clever, but it's not really. I'm still not sure what this is because I haven't applied my brain to it yet. But it looks like it's doing the same amount of recursion that I was doing, and I was hoping to get through this function without doing... Actually, it might be doing more recursion than I do. It might be doing more recursion than I do. Well, let's just try it with some values. Let's try it with n first and see what happens. How do I run? Where did the thing go to let me run the code? Where do I run the code? It went away. We didn't use my 120 minutes. This is lame. Okay, whatever. I'm going back to Sublime. We'll figure out this collaborative coding thing later. I don't know. I'm not smart enough to figure that out. What did I do wrong here? Oh. Parentheses. Nope. Nope. Bayer 2 should not return a value. Oh, yes, it should. ASCII characters are not allowed outside literals and identifiers. That's interesting. That must have been the website inserting some crap in here somehow. Oh, great. Is that what it was? What? Oh, yeah. That's definitely what it was. Good. Okay. Right sidebar. Oh, playback. Nope, that was the wrong button. I'm sorry. Cancel. Forget it. Forget about it. Pretend it didn't happen. Yeah, so that doesn't really give us what we want, does it? What did I come back here for? Oh yeah, I was going to turn this down. Let's see what it does with a smaller one. Yeah, it starts with 85. Definitely wrong. Is it done yet? No. It's almost done. Come on. No. Oh, oh. Stop. No, don't. Oh. I don't even view the... I was viewing the bunk. I'm still viewing the bunk. Run. So the top bar completely disappeared before for some reason. Who knows why. And now it's back for no reason. Alright. So it's running the code. It's taking a while. Well, we already know it's wrong, so who cares? So let me try and stare at this math for a little bit and see what it's doing. Hey, 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 hey. Don't bark. Sit down. Sit down. I'm trying to stream. So it takes x, left shifts it by the level, and then mods that by 2. That doesn't make any sense, does it? A recursive function is an infinite loop. This will not infinite loop because come on. Because it decreases the value of level by 1 every time, right? So it starts. I put n into it, which I don't really know what to put into it. It doesn't matter, because level. And then when it calls the recursion, it says level -1. So eventually, if I put a positive number in there, it will get to 0. Like it'll get to 0 eventually. And when that happens, it doesn't recurse. It just returns number. So it shouldn't be... maybe I don't understand what you meant because you said recursive function instead of a regular recursive function. I don't know what the difference between a recursive function and a regular recursive function is. One is extra recursive. So the only way that this mod 2 will return something other than 0 is if level is 0, which I guess makes sense. So this will be 0 unless you are at the highest level of recursion. So you add 1 to that. And then you take the y coordinate, do the same thing. Did I get it wrong somehow? This doesn't look like it does anything. Y left shift by 2, and then mod it with 2, and then multiply by... oh, yeah. No, I put this in the wrong place. Yeah, it should be like that. Oops. So the thing that gets modded by 4 here is the entire... all of this gets modded by 4. I'm pretty sure. So let's track the brackets to make sure I have the brackets properly. This one goes here, and this one goes here. This one goes here, and this one goes here. So yeah, all of this gets modded by 4. This by 2. This by 2. Yeah, I'm not used to this Mathematica syntax. Okay, so that's an improvement. Now we get the same crap now. Okay. So this again is 0 unless the level is the level is bigger than 0. So that will be 0. And then we multiply it by 2 and then mod it by 4. Maybe we multiply by 2 and then add it to all this crap and then multiply it by, and then mod it by 4. No, actually, aren't you shifting left instead of right? I am shifting left instead of right. Oh my god, you're right. It should be a bit shift right. Good call. Usually I only bit shift left to like take powers of 2, and so that caught me off guard. Okay, well, they're now different wrong numbers. Oh, wait, no. Oh, so we have a 1 on the bottom right here, which I think was actually his pattern. 1, 5, 9, 13. Now, this looks closer, actually. This looks closer. Yeah, it looks like everything... It looks like I called it the increment in my version of the algorithm. The increment is off. So there's another thing I'm doing wrong here. And maybe it's just this. I could just be passing the wrong thing in. Good spot with that right shift. So then all of this is doing then is it's getting the nth bit in the of the x coordinate, right? So let's go to the drawing board here. I want to make sure everybody understands this. You have some kind of number here. So we're going to right shift it by n and then take that number mod 2. So let's say n equals 0. Oh my god. N equals 0. Okay, then we're going to right shift it by 0, which does nothing, and then mod it by 2, which chops off all of these numbers. So that's what you do. When you mod it by 2, basically you take the rightmost bit, which chops off all the left numbers. So if n equals 0, you don't right shift it, and then you just get this number right here. If n is 1, then you right shift it, you get this, and then you mod it by 2, which chops off all the numbers on the left, chops off all the numbers, and then you get this bit, right? If n is 2, then this bit is over here, and all these get chopped off. So when you right shift and then mod by 2, it just picks the nth bit from that number. So that's what that's doing. So we get the bit that corresponds to our x coordinate and the bit that corresponds to our y coordinate. So the bit that why do we care about that though? Let's see if he talked about this in the article any before I go like crazy with this. Oh, okay. Not quite sure what he means by this part. But I definitely see what he's getting at. Where was the matrix? I actually have one of the matrices here to look at as I study his little formula. 0, 1, 2, 3. See, he didn't define I. So I'm not sure if I is a block matrix or if I is like a value. I think it's not a block matrix because it's not true that, oh wait, it is true. Oh, look at that. Like this submatrix right here is equivalent to this submatrix, except all of the values here are 1 greater than all of the values there. And then likewise with this guy, all of its values are 1 greater than the values here. And then likewise by this guy, all its values are 1 greater than the values there. So that's probably what he's doing. So this is a block matrix right here. It's the matrix of the previous iteration times 4? Plus 1. Yeah, no, I see that. Yep, that's it. That is it. So let's do it his way. Let's do it his way. I think I understand his way. All right. We're going to start with a 1 by 1 matrix. Okay. We're going to call it I1. Okay. I'm going to call it B1 because it's a bare matrix. B1. Now let's go to B2. All right, so by his formula, we're going to have 4 times B1 plus 0, and then 4 times B1 plus 1, and then 4 times B1 plus 2, and then 4 times B1 plus 3. So B1, so, you know, I take this matrix and then dump it in here as a submatrix of the larger matrix. So replacing that, of course, this is just 1. So I'm going to get 4 times, actually, this should start at 0, shouldn't it? So we start at 0. You have to start at 0. It throws the whole thing off. So 4 times 0 is 0. And then here we have 4 times 0 plus 1, which is 1. And then 4 times 0 plus 2, which is 2. And then 4 times 0 plus 3, which is 3. So that's B2. Now let's do B3. So that's a 4 by 4 matrix. All right. So this will be 4 times B2 plus 0, and 4 times B2 plus 1, and 4 times B2 plus 2, and 4 times B2 plus 3. And now let's start substituting. So 4 times B2, so I have to take each one of these and multiply by 4. So that will be 0, 4, 8, 12. And we add 0 to all of them, which we already did. Otherwise, in other words, did nothing. So now I'm going to multiply all of these values by 4, but then add 1 at the end. So 0 times 4 plus 1. 1 times 4 plus 1. 2 times 4 plus 1. 3 times 4 plus 1. And now 0 times 4 plus 2. 0 times 4 plus 0 times 1 plus 2. So that's 1 times 4 plus 2 is 4, 5, 6. 2 times 4 plus 2 is 8, 9, 10. And 3 times 4 plus 2. 3 times 4 plus 2, 12, 13, 14. Yeah. Yep, so this looks good. And now 4 times B2 plus 3. So I do the same thing, but I add 3. So here's a 3, and then here's a 7, and then here's an 11, here's a 15. So this recursion works to create the same exact formula. No surprise there. But with this recursion, it makes it a little bit easier to, like, now we can iterate this way. And for, like, we can develop a closed form formula for this coordinate right here. Like this the ijth coordinate, and that's what he has right here. He has a closed form formula for the ijth coordinate. That's pretty neat. So that means I still don't know what level to pass in here, but I'm thinking it should be. Let's try this. Let's just try passing in n-1. I'm thinking that's it. That's probably it. Yep, that was it. 0, 1, 2, 3, 4, 5, 6, 7. Yeah. So of course his process gives him his matrix is a different order, but it's all the same. Like the dithering will turn out the same. Well, you know, it won't be the same, but it'll be basically the same. It'll be the same idea there. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So that looks good. So let's see if we can redevelop. Yeah, no, not the dimension, but the it's 2, like 2 to the level is the dimension, I think. Algorithms fight. You probably want to see me run both of them a million times, or yeah, run a 256 matrix. Okay, let's do that. Let's kick it up a notch. Let's do it. Let's have some fun. What are we here for after all? Wait. Man, I'm gonna make it. I'm gonna increase the size a little bit. Not as fast. Algorithm fight. It'll be fun. Okay. Because you know it's exponential, it'll get big really quick. I don't want to. Actually, I should probably do this. It's probably fine. 7, 8. All right. 9. 2 to the 9. What is that? 2 to the 9 squared. That's 512 by 512. It's a pretty big matrix. It's getting big. All right. This is going to be a 1024 by 1024 matrix. Still pretty fast. Let's jump right up to 12 here. Oh wait, I didn't recompile that time. Seg fault. All right. So this algorithm seg faults at n equals 11. So let's just keep it to n equals 10, which takes 0.144 seconds. Yeah, I should enable optimization, but I think that will just compile the whole program away. So I don't want to do the. Oh, I see. So keep the printfs you're saying, so that it doesn't optimize everything away. It's a good idea. Yes. So that still takes a little longer though. 0.31. Yeah. Like if I remove it entirely. Yeah, it's still bound by the printfs, I think. But you know what I can do is A2I args. Ah man. You can't type when you're on stream. It's just not possible. Oh, that's why it crashed. I should probably malloc this. What am I doing? And you know, you gotta free the mallocs. That was probably my crash. It was just running out of stack space. Okay, and now I'll just do one printf at the end. Where I print a random entry. I have an Undertale song stuck in my head. Print a random entry so it can't optimize anything away. I think that should work. Let's see. And undeclared identifiers. A2I. So we need stud lib. Stud lib. Let's try it again. I have to do this number right here. Oops. Let's try it again. Alright. It builds now. Running it. Seg fault. I screwed something up. Oh, of course. Great. Hopefully that means it didn't optimize anything. Yeah, looks good. So that's getting slower and oops, slower and slower. Oh, that was perceptibly slow that time. Oh, half a second, 0.6 seconds. And now it takes a lot of seconds. Okay, so 2.712 seconds with his formula. Now, let's see, with my formula. Oh! Oh, snap! Oh, but our answers are different. Oh, no, that's random. It gives a random one. Oh, mine is way faster. Way faster. I was expecting it to be a lot slower. That's so interesting. I just want to make sure that they both do give the same answer here. Okay, and no, they give different answers. Okay, so something's wrong. Something's wrong. Oh, I wish I hadn't deleted all those printfs now. Let's get the printfs back. Oh, that's true. My matrices are rotated. Yes. Yes, they are. So that would definitely cause that. All right. Can I rotate mine? Should I? I could just rotate mine to match his. Not that hard. Maybe I can rotate his to match mine? I don't understand his formula well enough to rotate his to match mine. So I think I'm going to rotate mine to match his. Because I'm paranoid that we're not getting the right answer. Like, there's something wrong with my algorithm. So let's see here. He starts here. And then comes up here. He goes here, here. And, you know what, let's just run his algorithm for low value. See what he does again. 3. No, 1. So he goes there, 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 there. Okay. I think these two might be reversed. Well, we'll try it like this. Done. I think that should do it, yeah. Okay, we'll try it like this. I might still have to reverse it. They're both recursive algorithms. Which one do you mean? Oh, yeah, you mean his. Because his is not memoizing. For each level in the recursive algorithm, you're doing the same calculation 4 times. Yeah, I think you're right. I think it's calculation bound. Oops. So 0, 1, 2, 3. That's mine. Oh, wait. No, that's his. That's mine. What's his? 0, 1, 2, 3 is his. What the hell's going on here? Okay. Switching it back to his. Build, run. 0, 1, 2, 3. Okay, so this is his. So here's mine. 0, 1, 2, 3. Okay, good. Now ours match. So now I can get rid of this print stuff. And kick it up to a really big matrix and make sure we have the same answer. Yes, same answer. Good. Either we're both right or we're both wrong for for that entry. His is more apt to be run in parallel, though. That could be. No, I can run mine in parallel. Oh wait, when you say his, you mean mine, or whose do you mean? You guys gotta work on your pronouns. I don't see why mine couldn't be run in parallel though, because, like if you're parallel 2x, then you just start parallelizing at the second, like at the second entry of the, you know, at the second level of my recursion, you can start parallelizing there. If you're actually, you would parallelize 4x there, right? Send each one of these to a different processor or a different compute node. This one obviously can be really easily parallelized. You just pick what you want to do. I mean, like, what? Merge sort can be parallelized, right? Except for the very last merge step. You can, you know, you have your entries in your list. Pretend that these are all entries. And you can cut the list in half and say, okay, one compute node sort this one, the other compute node sort that one, and then you still have to do the final merge step at the end in series. But you can do the same thing with this algorithm. You can parallelize it, you know. You can parallelize it 4x, just send the 4 top level and then merge the results in series. And it should still be a lot faster. But yes, with his, you can put each pixel to a different node. Or, you know, each block. You don't want to put each pixel to a different node, but each block of pixels to a different node. Which is exactly what a GPU is, right? It's, you know, a different, not each pixel, but like each block of pixels gets a different, like execution unit. So, but you don't want to be generating Bayer matrices on the GPU if that's what you mean. I don't think you want to do that. You want to put them in a texture, or not even in a texture. You can just put them in you can load the matrix into static memory in the shader, right? You can do like, you can write this in your shader and then start putting values here. That's the whole point of why I'm writing this this algorithm, is so that we, you know, now you can generate an arbitrary size matrix the goal is we're writing Bayer matrices which are used in dithering, which are used in rendering a lot. And there's a link in the description that talks about Bayer matrices. In fact, let's go back to that page now that we've written a bunch of algorithms. Let's go and actually like see them in use now. We're not. I was hoping to get around to compilers, but we're not going to get around to compilers tonight. We'll have to save compilers for next week. What's interesting and quite limiting about Bayer is that due to recursive nature, signal difference is maximized only in this small 2x2 neighborhood. So larger Bayer matrices add more intermediate steps and values, but don't contribute much to any visible pattern difference. That is interesting. Therefore, most game engines I've seen have used up to 4x4 Bayer pattern with 16 distinctive values. So interesting story at work, where I work, which is at a game company. One of the rendering guys came to me and was like, you like math, right? I need to generate a larger Bayer matrix because I was using a 4x4 and that didn't work. And then I went to an 8x8 and that didn't work either. And so I needed to go to a 16x16, but 8x8 is the largest that he could find, like largest Bayer matrix that he could find sitting around on the internet. And there was no, like, before a few days ago, there was no general purpose formula for rendering them, for like writing them. So that's why we did that, and now we can generate them at an arbitrary size. But he actually needed a 16x16 Bayer matrix, or else he was getting, I don't know, I don't know, he was getting artifacts of some kind. So if you plot a periodogram, a frequency spectrum of it, you will clearly see only two single very high frequency dots. That's interesting. So here's one on the very top left, and here's one on the very far left. I'm not sure what those frequencies correspond to. Obviously, signal has some other frequencies, but with much lower intensities. Plotting, oh, I see. Plotting at a log scale fixes it. So the signal itself has a lot of frequencies at a very interesting distribution around the origin here. So I believe the origin is the lowest frequency signals. I believe that's how to read this. And the farther out you get, like this frequency is, or this part of the image has, no, let's see. These are low frequencies, and out here, these are high frequencies. I'm really bad at reading. I'm not a graphics programmer, no. I'm just a regular game programmer, but I like graphics programming. It's fun. I don't know. It's a hobby, you know. Let's go to the board. So we're going to go from the time domain to the frequency domain, okay? If you have a perfect sine wave, then you have exactly one frequency in your signal. There it is. Perfect sine wave, one frequency. If you have something like this, I tried to draw that so that it was like there are maybe 2 or 3 frequencies in here. One is about half of the other. Maybe I'll draw one more for kicks. Okay. So there are a few frequencies mixed in here. And then if you have something like the human voice, then it probably is crazy. You know, it looks something weird like that. And then like the frequency spectrum is not just isolated peaks, but you might have like some, you know, you have a lot of mid frequencies, maybe some high frequencies that are like the percussive punctuation sounds like puh. You don't really have that much low frequency in human speech. I don't think. I'm not an expert on this, so I might be saying the wrong thing, but there's a distinctive pattern of frequencies in human speech, right? So the way to read these plots in 2D is that high frequencies are here and low frequencies are there for this waveform. And so that's easy enough. So this is the same thing as before, but in 2D. So like this plot down here of frequencies is what you're seeing here. And I'm pretty sure that the low frequencies are in the center. So the closer you are to the center, hand-drawn FFT. Love hand-drawing FFT. I feel like I've drawn this same picture 1,000 times in my life. I don't know. So yeah, I think the low frequencies are in the center and the high frequencies are on the outside. So like the frequency of any particular point is the distance to the center, where higher is better. But I don't know what that means for like what is the angle? I don't know what that means for that. Because obviously like you have some interesting frequencies at some angles, and you don't have any interesting frequency. Like at this angle right here, you don't have any frequencies at all. So I don't know what the deal is with that. So on the one hand, Bayer matrix has lots of high frequency. That's perfect. And that's these high frequencies right here, because they're far from the origin. Not as much in the center. You see what there is in the center is darker than what there is on the outside. However, the presence of a strong single frequency bands tends to alias it heavily and produce an ugly pattern look. Yeah, so it does that. I mean, I don't know. This pattern is probably I don't think it's that bad, to be honest with you. It is a pattern, and generally you want to get rid of patterns. Like that's what he's saying. Like since the frequencies are like this, you know, you just have a few strong high frequencies, meaning that you can visually tell where those frequencies are, just like when you're listening to if you right, there's only one frequency there, and that kind of cuts through. I'm clicking a glass. That hurts my finger, so I won't do it anymore. Yeah, totally. You can pick whatever matrix you want, and then that gives you different properties as far as like what happens when you dither with it. For example, a halftone matrix. And I think he talks about halftone matrix in earlier versions of this article. Not earlier version, but earlier parts of this article. If you've been long enough playing with computers, remember 8 or 16-bit color modes and palletized images, this will look very similar. Yes, it does. It's cheap to apply, yep, because there's only a single lookup. So you do the single lookup, and then you just do a comparison and say, you know, like if it's higher or if it's lower. And it has your optimum high-frequency content. At the same time, it produces the very unpleasant patterns. I think in practice, you could probably get some better matrices. This is like a okay, someone in chat just linked a cool. Yeah, let me go to this link because this link looks good. Yes, it's an in-house rendering engine. Half-toning patterns. Okay, here we go. Yeah, you could pick whatever matrix you want, and I guess the Bayer matrix is kind of a first stop. You do that, and then you can try and optimize it later. But it's a pretty good approximation of what you want. Here's an 8x8 Bayer matrix, and you can kind of see some patterns right here. Here's a 4x4 Bayer matrix. You could definitely see a bunch of patterns. So the higher you get, I wish they. So this is an interesting two images because like you can compare here the difference between the 4x4 and the 8x8. And actually I kind of like the 4x4 better, to be honest. Like you can see like these lines. This is like a clearer line right here, whereas this is a little more scattered. I don't know. I guess it depends on where you look. Maybe there's not that much of a difference here. I wish they had gone up to 16x16 for this example, but they didn't. So that's ugly. Okay, so here's the halftone matrix that chat was talking about. I think it was Jeff. I'd prefer not to say which company I work for because they're really picky about what I say. You know, online. So I can tell you what game projects I did before I worked at this company, which was just type into the chat here. Actually, wait. I think you could just scroll down. Scroll down. It says who are you, and it says some things I've done. Oh, interesting. So here they took an 8x8 Bayer matrix, which is what we've been working on. But then they perturbated it, which I believe means they just moved it one way or another according to a random distribution. And you can see they got rid of a lot of the patterns, but now there's a lot of noises in it. I'm not sure that I would pick this over the 8x8 image that we saw before. Like I think this is better than that guy right here. It's very noisy. This is very interesting. Non-regular dither tiles. Oh, I see what they're doing. Yeah. And then they just tile these. So you take this pattern right here, 0, 1, 2, 3, 4, and then you just tile it over and over and over. You repeat it. And it gets you, it's all right. And then you get more complex patterns, and then it, yeah. See, the more complex you get the patterns, like the less it breaks up some of the patternness to it. You can see this, you can see these lines right here, and the lines start to go away. So that's nice. Wow, they're getting really into this. Supercell dithering consists in creating bigger dithering tiles from base tiles. Just like Bayer matrices, non-rectangular tiles can be used to recursively create bigger patterns, which is what we're doing. Oh, I see. So it's the same thing with Bayer, where you repeat the tile here, 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 and then here, but just add one each time you do. And actually, that gets a pretty good result. Take your pick. These are all pretty good. I think I'm liking this one the best, actually. So, okay. And then this gets more complicated. Void and cluster method. I'll check that out later. Interleaved gradient noise. Let's see what this is. The next sequence that this is what? This guy must not be a native English speaker. The next sequence that works extremely well for many dithering-like tasks is interleaved gradient noise by Jorge Jimenez. It's extremely simple. Oh yeah, no, I've seen this. You see this all the time in shaders. Yeah, this is a real a dead simple way of. Okay, so the problem is in the GPU there's no random number generator. Yeah, the ones before were like Tetris. I was just thinking that. There's no random number generator in a GPU, and so if you want something that looks random, then you have to use math to get it. And this is a really simple formula that generates basically good. It's not completely random, but it's pretty good random looking. You take this x and y, which usually you just pass the UV coordinate of something into this thing. So pretend that this is the U and V coordinate of a texture, and then you multiply the x by this and the y by that. You do the dot product with this silly vector. Take the fractional part of that, multiply it by a big number, take the fractional part of that, and then he chose these constants very carefully. Like if you choose different constants, this doesn't work. You have to hash stuff. What do you mean by that? I've tried jiggering around with these constants, and if you do the wrong thing, then none of this, it suddenly doesn't look random, or you'll get weird patterns that aren't very you'll get low frequency patterns in there that you don't want. So I don't know what he did to pick these numbers, but it's pretty cool. What's even more impressive is that such pleasant visual pattern was invented by him as a result of optimization of some common web knowledge hacking noise hashing functions. Oh, that's what you mean. Unsurprisingly, this pattern has parallelogram containing frequencies that correspond to those interleaved gradients. Ah, it's true, it does. And they're frequency aliens. So this frequency diagram looks a lot like the one that we were using, the one that we looked at before. Oh, yeah. You can hash stuff. And that's basically what he's doing. That's what he's doing, I think. I mean, not in the typical sense of like you typically think of hashing a string, but sort of, I suppose. I guess it's like a 2D hashing function or something. So Hodhan, I think you mean Jimenez, is a COD programmer. If you recall correctly, he presented at SIGGRAPH. Cool. He said optimization here, and I'm wondering if he meant like numerical optimization. Like he ran these numbers through an optimizing algorithm that looked for like the proper, like he optimized on the proper distribution of noise here or something. That would be interesting to do, to see if you could get get even better numbers than this that produce better blue noise. Yeah, I certainly didn't present at SIGGRAPH, that's for sure. Just like with Bayer, these frequencies will be prone to aliasing and resonating with frequencies in the source image. But almost zero low frequencies give nice, clean, smooth look. Yeah, it does look pretty good. And it's not aligned, like Bayer's aligned. Bayer looks like it's aligned up and down like this. This guy doesn't look so aligned. He kind of looks like his alignment for some reason is a little bit off center. I think that's actually what this is, a dot product. So let's see, 0.0067 and 0.00058. So what he's doing here is 0.0067 x plus 0.00058y, right? So this is sort of the same thing as saying 0.0067, 0.0058 dot product with xy. So then what does this mean? You know, you have your xy vector, it points somewhere. And then there's this 0.067, not 0.0067, 0.067 and 0.0058 vector that you're dot producting with. So let's look at what that looks like. Wolfram alpha is probably the fastest way to render a vector. I'm not sure. We'll see. Come on, Wolfram alpha. 0.067, 0.0058. I've probably mixed up those numbers now, but it doesn't matter. Okay, so you can see that this vector is mostly, I guess it's mostly along the x. Well, hold on. This 0.068, yeah, no, I got them right. It's mostly along the x and a little bit on the y, so it's kind of like it's mostly aligned but not quite. So that corresponds to, no, not quite. This is maybe at a tiny bit more of a tilt than this vector is. Yeah. Well, maybe if you think about it this way, going the other way. No, I don't see any lines going that way. It looks like the aliasing is. I was hoping that the aliasing here would correspond to the aliasing of this vector, which it might. There might be some kind of association there, but it doesn't look like it. To the naked eye, it doesn't look like it, which is too bad. Okay. Let's finish this up. Finally, we get again to using blue noise pre-generating pattern. Yeah, so to be honest with you, like I've done both of these things. I have used this formula in a shader, a hashing function, as Jeff says. And I have also, like, you can just generate, you can go into the GIMP or whatever and generate noise and then save it to a texture and use that instead. And both work fine. So Yeah, like if you want the noise to change over time, then that's different. But so let's see. To recall from previous part, blue noise is loosely defined as a noise function with small, low frequency component and uniform coverage of different frequencies. That's right. In other words, blue noise, if we look at it in our frequency domain, blue noise looks like this. All of your frequencies are on the high end, and you know frequency, but you have all of the frequencies in the high end. It's noise. Like there's no, like you get above a certain part and it's just flat. There's no signal here. So that's blue noise. Anyway, that's what the frequency distribution looks like for blue noise. To generate a simple 64 by 64 wrapping blue noise like sequence, which took him apparently a couple hours on an old MacBook. And it has the following periodogram. Yeah, so look, see how the values close to the origin, which is in the center, are dark, meaning the frequencies there are high. So there are not many low frequencies in this. And here's the visualization. So let's see. So this is the frequency spectrum of white noise versus blue noise. So you see white noise it has all frequencies present, and blue noise has only the high frequencies present. There are no low frequencies present. At the same time, it doesn't have linear frequency increase for higher frequencies like audio/academic definition of blue noise. I'm not sure if it's because my implementation optimization only 7x7 neighborhood is analyzed or the original paper, but it doesn't seem to impact the results for our use case in a negative way. Fair enough. So this is, he just takes so he's not even using a Bayer matrix now. He's just doing the dithering with a regular noise matrix. So that's interesting. That's a 64 by 64 pattern, but optimized for wrapping around. So border pixels. Oh wait, if this is a 64 by 64 pattern, then it should repeat every so often. And I'm going to look for a pattern here. No, I don't see it repeating anywhere. I'm looking for this guy right here. Oh, so maybe this whole thing is 64 pixels. That could be. That's probably it. All right, fair enough. So where were we? In this gradient, it's repeated 2 by 2. And this is how it compares to white noise. So I wish you would tell me which one's white and which one's blue. I assume that the one that looks better is blue. And that's what he says. Because of high frequency contents only, you can't see the problematic clumping effect. So he's saying this one's blue and this one's white. So because the white noise has a lot of low frequencies, then it sometimes will cut out. Like you can see there's a cutout right here where there's a lot of there's a big depression, right? So if in your time domain you have a lot of things going like this, then in your frequency domain you're going to get, this is low frequency. Even if you have a lot of high frequency layered on top of it, right? But what we want is only the high frequency part and not the low frequency part. So these low frequencies look like large hills and mountains and stuff. And that's what you get for, see this big scoop right here? That's like a big valley. And, you have areas over here where there are like, I don't know, they look like mountains here, right here. Right there, there's like a lot of, there's a clump of lighter stuff right here and maybe right there. And that's where the low frequency noise is creating large craters and large mountains, like in the signal. Whereas with the blue noise, where they're only high frequency, there are none of those larger features, and so you have more of an even spread. So that does look a little bit better. It also means that if we oversample, like with all those new fancy high resolution displays, and then blur it or apply temporal blur, then it will be more similar to the original pattern. That's true. Blurring can go a long way. So you blur the noise and that gets rid of even more of the low frequency content. And because a blur is basically the same thing as a low pass filter. Wait, I just said the wrong thing. A blur is a low pass filter, yeah. So check this out. So here's the time domain. And here's my signal. Okay. Here's the frequency domain. I have a low frequency and I have a high frequency. Now let's say I do a blur on this thing. Then it's going to look like this. Right? Just a small kernel blur. Then I've smoothed out all of the high frequency stuff. And so it's gone. And so now I only have the low frequency stuff, and the high frequency is, almost not there. Or maybe completely gone. So remember that the original photo was just a smooth gradient. It had no high frequency at all. It just had one large low frequency thing. Just one big smooth gradient. So when you apply that blur, you get rid of a lot of the noise that you added, which was an attempt to get rid of the banding. And while I said we will not be looking at triangle noise distribution for this post, I couldn't resist the temptation of comparing them. White noise versus blue noise with triangular distribution remapping applied. And I've never heard of triangular distribution remapping, so hopefully he makes another post and I get to learn about that. So we compare all of them. White noise, blue noise, Bayer, and interleaved gradient noise. And then with the triangular mapping. So that probably sums it up here. Final recommendations, let's see what he says. Whenever possible, avoid ordered Bayer. Many game engines and code bases still use it, but it produces many visible unpleasant patterns. Okay, well we put in all this effort to learn Bayer, and this guy doesn't even recommend that we use Bayer. Well, we learned some things, even if, we even learned like non-Bayer related things, so. And he could be wrong. Or he could be right. If you cannot spare any memory lookups, but have some ALU, use excellent interleaved gradient noise by Jorge Jimenez. That was the formula with the dot product in it. It produces a much more pleasant patterns and is extremely cheap with the GPU instruction set. That's true. However, patterns are still noticeable and it can alias. Blue noise is really great noise distribution for many dithering tasks. And if you have time to generate it and memory to store it and bandwidth to fetch it, it's the way to go. White noise is useful for comparison and ground truth with pixel index hashing. It's easy to generate, so it's useful to keep around. Oh yeah, I've seen that article. And then there's a summary. So great. So that was a lot of fun. And now I'm going to start wrapping up and winding down for bed here. So thank you everybody for joining me. That was fun, Bayer matrices. I think I'm going to take the code that I wrote. Because it's so much faster than his, I'll just put it on GitHub and something like that. So now this code will exist. I'll clean it up a little bit first. I'll do it in the morning though. And next time, I think we're going to do compiler construction. So here's the thing. We've all seen my math videos. I think probably like a lot of us have seen my math videos. And I have an idea for how to make better math videos than that, which are actually interactive web pages. And an integral part, this is like a teaser for next time, an integral part of the interactive web page is that you can program in the web page, and as you program, the vectors that you're manipulating in the program will show up in like a 3D space in the website. It's going to be super cool. This is my idea. So as an example, the teaser for next time. Next time on my stream. So like if you say vec3a, then over here, a big vector appears that says A. Okay. And then you say vec3b. Over here, another big vector appears that says b next to it. Okay. And then if you add them, if you say vec3c equals a plus b, then another vector will appear over here that is the sum of the two. And then you can take the cross product, and the cross product will appear in the dot product, and the dot product. Like, everything will appear on the left what you're doing over here. And then, even better, you can click this thing and move it around, like move this vector around, and then it will update over here. It will be like, oh, you moved it was a 1, 2 vector, but then it will update. You changed it to like 3, -2 or something like that. So both sides will affect each other. And that will be a tool for learning. Like, I'm going to redo all my videos with that. And I'm also going to do geometric algebra and all these other cool topics. But in order to do that, I basically have to write a new programming language, because none of the existing programming languages satisfy all the constraints that I need to have for this thing. So next week, we will be writing that programming language that will power this interactive web thing. Which I'm really excited about. It'll be a lot of fun. I've already made some headway into the compiler. I'm not going to go too much farther, though, because I don't want to like get seriously into the compiler and then lose the stream. Like, I want to start from the basics. So next stream, compiler construction, we're going to learn all about it. We're going to learn all the stages of compiler. If you never took a compiler construction class in college, it doesn't matter, because you'll understand it all by the end of next stream next week. So hopefully people come. So good. I'm going to log off now. Go to bed because I'm tired. I've been talking for 3 hours. Thank you, everybody, for coming. I hope you had a good time.